In our previous lectures, we talked about a method that we call backstepping to design control law to stabilize the origin of the closed-loop system, where we use Lyapunov's theorem to help us in our design. Okay. So in that context, the system that we controlled was a system with an input, and that input was a control input. Okay, so in a sense it was the good guy, because we can choose whatever input we apply to the system, and we choose such an input that the the system under that input behaves in a desired way. Today we will look at the input from another point of view. We will study input to state stability, and in this context, input is not the good guy as in the previous lectures, but it's the bad guy. Okay? By which we mean it represents the undesired and usually unpreventable, and we cannot foresee it. Okay, disturbance to the system, like the bumps in a room on a road. Okay, so that those bumps they affect negatively the smoothness, the comfort of the ride. So they represent the undesired disturbance to the system, or the noise in the measurement would also be an undesired input to the system, where the system is a closed-loop system where you collect the feedback information through measurement. Okay. So what we will do in this lecture is we're going to introduce the definition or the concept of input to state stability, and we will talk about the relation or implications of that definition on the evolution of the system, okay, in a qualitative sense, and also in particular we'll talk about its implication on the asymptotic stability of the origin of the system. Okay, but first we have to, before even defining input to state stability, we need to motivate that definition. Okay, and the motivation comes from the linear systems. Okay, so consider the linear time invariant system. X dot equals AX plus BU, where the matrix, the system matrix A, is Hurwitz. Okay, so therefore this system is stable in the sense of Lyapunov, or equivalently, all the eigenvalues of A are with strictly negative real parts. Okay, that is all the eigenvalues of A satisfy they are on the open left alpha plane. And then about the input U in Rn. Okay. Input is also in general a vector, represents the undesired disturbance. As opposed to control input of the previous lecture. So nominally or ideally, you want the system to satisfy X that equals AX, where A perhaps is representing some closed-loop system matrix, but we have to, for practical purposes, we have to take into consideration also this term, which represents the outside disturbance coming from the environment of which the system is a part. Okay, and what we want to analyze is how badly this undesired input would affect the nominal, the ideal evolution of the system. Okay, x that equals ax. So that's our question. The effect of input on the ideal or input-free or disturbance-free behavior. Now, why the input-free behavior is that is the norm of x is going to 0, or this state or the solution is converging to the origin? Well, it's because if you remove the input, you have x that equals ax, and all the eigenvalues of a are on the open left half plane. Therefore, the solution, no matter where you start, is converging to the origin in exponential fashion. Okay. Now, what we want to see is how this disturbance term affects that convergence to the origin. So let's write down the solution of the system, which we can write explicitly because the system is linear. Remember that we cannot write explicitly the solutions for a general nonlinear system. Okay, the solution reads x of t equals e to the at. Okay, that's our state transition matrix times the initial state. Okay, so this would be the complete solution if we didn't have any disturbance. Okay, so that's the solution in the ideal case, the disturbance-free case. But we do have disturbance in our system, or at least we want to take them into consideration. Therefore, the solution will not only depend on the initial condition, but also the input, clearly. And that effect or the input manifests itself through this integral, e to the a t minus tau bu tau d tau. Okay, so clearly the overall evolution of the system state depends on the initial condition and the input function that we apply, okay, throughout the interval from 0 to t. Now, since A is Hurwitz, okay, sometimes some people call it stable, okay, that means the norm of this matrix e to the at, which is that matrix function of time, so that can be bounded by some constant e to the minus lambda t. Usually, lambda is a positive number, and that represents that represents the distance of the most dominant eigenvalue of A, okay, to the g omega axis. And okay, for some positive constants k and lambda. Therefore, we can write x of t. Okay, so we're taking the norm of both sides, and then we can upper bound the norm of the solution by the norm using triangle inequality, the norm of this term and plus the norm of that term. And the norm of this term, because we have this inequality or upper bound on the norm of the state transition matrix, can be written as k e to the minus lambda t times the norm of the initial state or initial distance to the origin of the state, plus the norm of the integral, which is less than or equal to the integral of the norm. Therefore, we can write k e to the minus lambda t minus tau. Again, for the state transition matrix, we use this upper bound times the norm of B times the norm of the input d tau. Okay. That can be upper bounded by k e to the minus lambda t times the initial distance plus, now these are constants, we can take it outside integration, k e. Then we can take this outside integration by replacing it by its largest value that it takes between the throughout the interval from 0 to t. Okay, so therefore we have sup tau in 0 t u tau, and this sup just means, well, in most cases max, okay, maximum, but sometimes maximum is not attained, okay, so in that case this is more general function that we use, supremum function, times, okay, what's left is this term, which we integrate e to the minus lambda t minus tau, and then we can take e to the minus lambda t out of integration, because integration is with respect to tau, that's our variable, and then what remains is from 0 to t e to the lambda tau d tau. Okay, now this integral here is what? E to the lambda t minus 1 over lambda. Okay, now e to the lambda t minus 1 times e to the minus lambda t is never larger than 1. Therefore, we can upper bound this whole thing by k e to the minus lambda t minus lambda t plus k norm of b over lambda. This whole thing is constant. And then the supremum for the range 0 to t of the norm of the input or the disturbance. Okay. So let's call this inequality 1. Now, let's look at inequality 1 and interpret or figure out certain qualitative implications. Okay. One thing that's implied is if you start from the origin, suppose that's where you want to end up anyway, then so this term disappears because x of 0 is 0, and then what happens is the norm of the future values of the state or the solution is upper bounded by this some constant times supremum of the norm of the input. And if the norm of the input is small, if you have a small disturbance, then the norm of state, okay, norm of solution will also remain small. Okay, so that means for zero initial conditions, small disturbance implies small solution, small state. If you start outside origin, okay, and even if you start quite far from the origin, note that eventually, as time goes on, because lambda is positive and we have e to the minus lambda t, the effect of this term on the contribution of the term becomes more and more insignificant. Okay, and as time goes on, this becomes negligible, and again, the overall norm, the norm of the solution, will be upper bounded after some time, the norm of the, or the supremum of the norm of the input. Okay, and that roughly means that if, even for non-zero initial conditions, eventually it would mean that small disturbance would imply, after a while, small solution, small state. Okay, and that's the key observation which motivated people to define input to state stability, which proved to be a useful tool for analyzing nonlinear systems under disturbance. Okay, so let's write down our observations. Inequality 1 implies for zero initial state x0 equals 0, we can say, roughly speaking, small input implies small state. Okay. Small disturbance implies small state. And for arbitrary initial state, okay, for non-zero initial state, small input implies eventually small state. Eventually small state. Why eventually? Because initially this may be a large term, but because it's multiplied by e to the minus lambda t and lambda is positive, therefore this term is converging to 0. It's vanishing exponentially. Therefore, eventually the magnitude or the how large the state is will depend mostly on the magnitude of the disturbance. Okay, and then this behavior of stable linear systems, okay, exponentially stable linear systems, has motivated the notion of input to state stability. Motivated below definition. Okay, which may, well, I believe it's the definition is due to the Argentinian-American mathematician Eduardo Zonta, who had very important contributions to the area. Okay, so now we're ready to introduce our definition. It's definition 4.7 from the text. The system. Okay, now we are in the general nonlinear domain. X dot equals f of t x cubed. So we consider general case where the right hand side is allowed to depend on time also. Is said to be input to state stable. And we will generally abbreviate it to ISS if there exists the following comparison functions: a beta, a class KL function, and gamma, a class K function, such that norm of the solution, norm of the state, is always upper bounded by beta x initial norm t minus t0. This is how far we have moved forward from the initial time, plus gamma of super tau in t0 t u tau. Okay. For all future time, okay, t larger than t0. Note that if we compare this inequality to inequality 1, we see that the class KL function is this exponential decay function, okay, with respect to time. So we generalize that term here, which represents the the term due to, or the contribution of the initial condition, and also it represents, we see that that contribution becomes smaller and smaller as time goes on, and that behavior is captured by the class KL function here, beta. Remember that class KL function was such that it's class K with respect to its first argument, and when the second argument is held fixed, okay, and when the first argument is fixed, it's a non-increasing function with respect to the second argument, and eventually it goes to 0 as the argument increases. So that's a class KL function, and this is a class K function, and class K function was such that it's continuous 0 at 0 and strictly increasing. Okay. Also, if it's unbounded, then we say that function is class K infinity. Okay. Now, one direct implication of input state stability is that if the input is 0, then this term disappears. And what we have is the norm is always upper bounded by this class KL function. Okay? And that's the exact definition of global uniform asymptotic stability. Okay. Now, in a sense, what we're doing is we're generalizing that definition to cover the case where we have also the disturbance in the system. So we're also trying to capture the effect of that disturbance on the overall qualitative motion, okay, or evolution of the system. So let's put that remark down. If a system TXU is input to state stable, if it's ISS, then the origin of the system x that equals ftx0, origin of the, you can call it the nominal system, the ideal system, where the disturbance is 0, is globally uniformly asymptotically stable. Okay? Now, the reverse is true for LTI systems, but not in general. Okay? So the reverse is not necessarily true in general. That is, if you have a system x equals f of t x cubed, and if you fix u at 0, you obtain a nominal system, and suppose that the origin of that nominal system, disturbance-free system, is globally uniformly asymptotically stable. That does not imply that this system, the original system, where we have a non-zero disturbance, is ISS. Okay, it doesn't mean that the original system is ISS, and it's very easy to come up with a counterexample. Okay, let's put it down. Example. Okay, so this example will immediately show that the reverse is not true in general. Consider the scalar system x that equals minus x plus u times x. Okay, because here input and the state they multiply with one another. Clearly, this is not a linear system. For the input that's identically 0 for all times, the system becomes, or the nominal system is x that equals, okay, for u equals 0, this term disappears, so we have x that equals minus x. Okay, a simple first order linear system with eigenvalue at -1, so clearly everything converges exponentially to 0 with time constant 1, for which the origin is less, okay, globally uniform asymptotically stable. This system, however, is not ISS, input to state stable. Why? Because bounded input can result in unbounded state. Unbounded state. And this is not allowed by the definition of input to state stability. If the input is bounded, that means this term is bounded, and then the norm of the state, the norm of solution, is always upper bounded by something, because this is constant, and then this is never larger than its initial value. Then we can always upper bound, okay, x of t, the norm of x of t, by some number, be it a large number, nevertheless. The norm x of t cannot go unbound, cannot become arbitrarily large. Okay. However, with this system, if you choose, for instance, input fixed at 2, okay, let's say, then you have x that equals minus x plus 2x, so that makes x that equals x. And clearly the solution is initial condition times e to the t, so the solution is blowing up exponentially, and that's not allowed by ISS. Okay, take, for instance, u of t identically equals to 2. Then x dot equals x. Okay, this system becomes x that equals x. It's a linear system with eigenvalue positive. Okay, at 1. And clearly, unless you start at the origin, all other initial conditions will take you to infinity. If x0 is the 0. Okay, now let's see a more interesting example where we're going to use input state stability to establish the fact which is easy to believe, but it requires a little bit work to establish rigorously, which is that if the input is going to 0 eventually, let's say an exponential decaying disturbance, then the state 2 has to converge to the origin. Okay, so that's the claim of our next example, and we will try to establish that. It's a nice example of analysis. Okay, it's from the text. Example 458. So suppose that a given system, x equals f of txq, is ISS. Okay. Show that using the definition of ISS, of course. Then t goes to infinity, ut equals 0. If the input is converging to 0, then the state must converge to the origin. T goes to infinity, x of t must be 0. Okay. Now let's prove that claim. And when it's proof that we're trying to construct, there are many ways. The solution obviously is not unique. So if you don't like the way that we choose to establish this claim, you can always try your own better method to prove it, okay, to demonstrate it. So suppose for the system we're given an input that satisfies this convergence to 0, and some initial condition at some initial time t0. Okay, so let x t0, the value of the state at the initial time t0, and u of t, the input function. Suppose that those are given. Okay. Now what we know is, first of all, okay, let's write down what we know. We know that the system is ISS. Therefore, by definition, there exists a beta function, okay, class KL function and class K function gamma, such that the norm of the state is upper bounded by t minus t0 plus gamma supremum t0 to t u tau. Okay. So this is our first inequality, which directly comes from definition of ISS. Okay, so let's keep it somewhere. And then what we have that u of t is converging to 0 as time goes on. So that implies, or in fact it's equivalent to the following: for each k, 0, 1, 2, okay. Well, before that means the following. Okay. So suppose that this is u of t, t is the initial time. So that means that if u of t is converging to, okay, so this is the norm of u of t. If u of t is converging to 0, so that means you give me any positive number, okay, epsilon, and I can always find, okay, I can always find a time, okay, let's call it t, such that after that time t, the norm of the input will always be less than this epsilon. Okay. Now this epsilon can be very, very small, but it doesn't matter. I can always find a t that's large enough so that even though the input, norm of input does some crazy stuff here, eventually it has to settle down below that epsilon border. Okay, it can never leave, it can never go up that epsilon border for if you wait long enough. Okay, and then let's take that behavior and put it in a more structured, or express it in a more structured way. Okay, and u of t converging to 0 means that for each k here, we can find a time, let's call it tk, large enough, t0, such that norm of input can be upper bound by 1/2 to the k. Clearly, as k increases, this becomes smaller and smaller. For all t greater than or equal to tk. Okay, so we have not only a single epsilon, but a bunch of epsilons here, and each epsilon is, okay, we start with 1, and then 1/2, and 1/4, and 1/8, and so on. And for each of those epsilons, and epsilons are converging towards 0, we can find times, okay, large enough so that if you wait until that time, from that time to the future, the norm of the input will be less than the corresponding epsilon. Okay, so that's exactly what converging to 0 means. And finally, so let's give this number 2. This is our relation number 2, which we will use in our analysis. And then finally, x of t converging to 0 implies, or in fact is equivalent to, for each epsilon, we can find the time large enough, let's call it t of epsilon, because it depends on epsilon, larger than t0, such that norm of x of t less than epsilon for all times greater than or equal to that particular border. Okay, and let's call this relation 3 or identity 3. Okay, so we have put the claim in a more structured way now. So what we have is we have 1 because that's the definition of ISS, so that's what we're given. We have 2 because we're told that the input is converging to 0, and using 1 and 2, what we want to do is we want to establish 3. That is what we're trying to show is 1 plus 2 implies 3. Okay, so let's do that. Now, since this is what we're trying to show, and this is such that for any epsilon, we can find a time large enough so that this is satisfied. So let us be given an arbitrary epsilon. So given some epsilon, okay, positive. First, choose an index k, and k is a non-zero integer, such that gamma of 1 over 2k is less than epsilon over 2. We're calling this inequality 4. Now we can always find the k, okay, so that this 1 over 2k is small enough, and gamma of that number is smaller than epsilon over 2. Why? Because this is a class k function. It's 0 at 0, and it's also continuous. Since it's continuous and 0 at 0, that means closer we get to the origin, smaller this thing has to become. Okay, therefore we can always find a small enough argument so that gamma of that argument is smaller than what we want, epsilon over 2. So that's our inequality 4. Then, in our next step, choose another positive number n such that n is greater than or equal to x t0 tk minus t0 plus gamma of sub tau t0 to tk and then norm of the input. Okay. Now, here tk is coming from the previous step, so this is fixed. Okay, so this also is fixed. Okay, the initial condition because where x of t is given, and then since this interval is fixed, this whole thing is also fixed. Okay, so here we have a number. It can be a very large number, but it's nevertheless a finite number, and we choose an n such that it's larger than that finite number. And let's call this 5. And finally, choose delta, again a positive number, such that beta n delta is less than epsilon over 2. Okay, and that's our sixth inequality. Now n is fixed from the previous step, and now what we're trying to figure out is we're trying to figure out an argument, second argument, that's large enough so that this beta of n delta is smaller than epsilon over 2. We can always do that because when the first argument is fixed, beta is a class scale function, it's converging, this is never increasing and also converging to 0 as the second argument becomes larger and larger. Okay, so we can always find a suitable delta that satisfies that inequality. Okay, now how to combine all these? 1, 2, 3. Let's do that as follows. Okay, let me draw a line here. Now we're ready. Okay, we prepared our pieces, we prepared our bricks. Now we're ready to put those bricks on top of each other to make the wall of our proof. Now 1 and 5 implies x at tk, norm of x to tk, less than or equal to n. Okay. Now this holds true for all t. Okay, for all t larger than t0. So what we do is we consider a particular t, and that t is tk. Okay, t sub k. Plug in t sub k here and here and here. So what we have is here we have a number, and that number up or down is norm of x at tk. And what we did in step 5 is we picked a number already that would be larger than particular number. Therefore, x value of norm of x at tk is less than or equal to n. Okay, because it's less than or equal to what n upper bounds. So that's our 7th inequality. Then then using 1 and 7, okay, 7 is here, 1 is here, we can write norm of x of t less than or equal to beta n t minus tk plus gamma of sub tau in tk to t u of tau. Okay. Now why we can write that? Note that the system is ISS. Okay. Therefore, for any initial time, the norm of the state 4 times later than that initial time is upper bound that beta of initial state, and then t minus the initial time. Then we have that supremum. Now 7 says that the value of the state at time tk is less than or equal to n. Now what we're doing is we're invoking ISS property once again, but this time for the initial condition x at tk, and tk is our new initial time. Okay, so what we would have is x of t less than or equal to beta of x norm of x at t of k, but x norm of x of t of k is less than or equal to n, and beta class ki function is always a class k function with respect to its first argument. Therefore, instead of this norm, you can always put something larger, and inequality will still hold true. Okay, and that's what we did. That's what we did. We invoked, once again, we use ISS property, this time for the initial time tk and the initial condition, that x of tk. And then that's less than or equal to beta n t minus tk plus gamma of 1 2 to the k. And how we were able to write that? So this is for t larger than or equal to tk. And from the first line to the second line, what we did is we used this, okay, inequality or property 2. Okay, because we know that the supremum of the input larger than times tk is less than 1 over 2 to the k. Okay, that's how we defined tk in the first place. So that's why 2. And then that's less than beta n t minus tk plus epsilon over 2. Okay, and for that we use the inequality for my fault. And let's call the last of our inequalities, inequality 8. Now we're ready to write down the final line. Okay, let T epsilon be chosen as Tk plus delta. Okay, Tk is this Tk, and delta is how we pick, and that we picked in inequality 6. Then 6 and 8 implies 3, okay, that is x of t is less than or equal to epsilon for all times larger than t epsilon, because for times greater than t epsilon we have t less than or equal to, okay, that's 6, okay. Okay, we're using 8 now, okay, x of t less than or equal to beta sub t larger than or equal to t epsilon. Now we can choose any t, lowercase t, larger than tk, and what we're doing is we're choosing t to be t epsilon, okay. And then we're taking the supremum of class ki function and t minus tk, and by definition, because it's never increasing with respect to its second argument and the first argument is fixed, this supremum exactly equals, you plug in t equals t epsilon here, okay, plus epsilon over 2. That equals, if you plug in t equals t epsilon minus tk is delta, okay, so that equals beta and delta plus epsilon over 2, and delta was chosen such that this beta of and delta is less than epsilon over 2, so we have epsilon over 2 here, another epsilon over 2 there, so that is epsilon. Okay, so x of t, norm of x of t is therefore less than epsilon for t larger than t epsilon. Okay. And since epsilon was arbitrary, so that means x of t must converge to 0. And that's the end of our proof or end of our analysis.